Hey everyone, in this video we've got two things to do. I've got two sample AP problems for you. In one of them we'll discuss another definition of differentiability, and in the other one I'm going to show you, well, we're going to need to use our calculator to solve the other problem, so make sure you have your calculator ready to go by the time we get to the second page. Okay, so our first page here, this is a real sample AP problem. Now, for full disclosure, this would likely be like a part B or C of a real question. This would definitely not be a full question. Anyway, let's go ahead and read and solve it. So we have two tasks. Nope, we actually only have one task. I was getting ahead of myself. We are tasked with determining whether the function below is differentiable at x is 3. Well, differentiability really has two conditions. One, the function has to be continuous. So we first have to ask ourselves, is f of x continuous at x equals 3? Whoops. And if the answer to that is yes, then we'll move on to check, is it actually differentiable at that point? Does the slope exist everywhere around 3? So you've solved this style problem a number of times before. Basically, we just need to check, is the limit as x approaches 3 from one side equal to the limit as x approaches 3 from the other side? And is that also equal to the function's value at 3? If that's a true statement, the function is continuous there. So from the left side, we're going to use the left side function here. So that'd be square root of 3 plus 1 is 4. On the right side, we've got 1/4 of 3 plus 5/4. So 3/4, 5/4, 8/4. Wait a minute. Hey. Did you notice this? One, I don't know why my computer keeps scrolling down. And square root of 4 is definitely 2. Sorry about that. So there we go. So 8/4 comes out to 2. Okay. And then f of 3, well, we've got the or equals here, so we also know that is equal to 2. So yes, f is continuous at x equals 3. But that wasn't the question. The question was, is the function differentiable? Well, checking for differentiability is actually very similar to checking for continuity. To check for differentiability, you need to run through the exact same process, just using the derivative. In other words, you are checking to see, is the derivative continuous at this point? So again, notice how I'm making an effort to say f prime in all three of these places. Is the derivative continuous? So that's really what we're checking here. So before we can do that, let's find the derivative of this function. So let's see, f of x equals, there's two parts. Let's just take their derivatives separately. So square root of x plus 1, that's really the same thing as having x plus 1 to the 1/2, right? So we can still evaluate this using the power rule. Let's bring down the exponent of 1/2. Let's keep the inside the same and make sure you subtract 1 from the exponent. And that's wherever x is less than or equal to 3 still. And then for the second one here, it's a linear function, so we'll just have power rule on the 1/4 x, which will just leave us with 1/4 when x is greater than 3. So we're going to be plugging 3 into both of these and checking that. On the left side, we're going to be using the first one here, so that'd be what does, okay, pen stopped. Let's try again. 1/2. Oh, and maybe we should clean up that square root, huh? That's going to be messy to work with. Let's rewrite our derivative here so it's a little easier to work with. Let's get rid of that negative exponent. Okay, this will be nicer. So if we plug in 3 for our limit, we have 1 over 2 times the square root of 3 plus 1 is 4, which would give us, wow, I really squished this together, didn't I? 1 over 2 times 2, that give us 1/4. Let's check the second limit now. So on the right side, well, it's just 1/4. Nice. And then we've got the or equals on the first one. So we also know the derivative itself at that point is 1/4. So because all 3 of these were equal to each other, the function is actually differentiable at this point. And again, that is only the case if you get all 3 of these to be equal. Let's turn the page. So this is another real AP problem. This is definitely a free response problem. At most, now I've got a whole bunch of similar questions here, A, B, C. At most, you'd see 1 or 2 of these in a real AP question, and the other 2 parts would be like something else. Most AP questions have like 4 1 setup and 4 little questions built in. So, you know, we're going to have a lot of repetition here, but that's because I want you to know how to answer all the little parts, even if you only see 1 or 2 of them on the real test. So let's read it here. The rate at which snow accumulates on driveway in cubic feet per hour from time is 0 to time is 8 can be represented by this function, E. Okay, so let's just leave ourselves a note here. E of t is a rate of, and it says snow accumulates. So rate of snow accumulation. At t equals 5, Jill goes outside and begins shoveling her driveway. She removes snow at a rate of this function, cubic feet per hour. Okay, so R of t, it's again, it's a rate of snow removal. And then we have our task. Okay, so up first, our job is to interpret and give interpret the meaning of and give the value of the E function evaluated at 5. So here's where you needed your calculator. Let's go over there and let's punch those in real quick. And my suggestion would be just punch in both the equations on the same graph. Just so that way they're stored in your calculator somewhere. So we'll make F1 the E. So let's do, I have to hide you. So let's do square root of, now let's use x instead of t just so it's easier here, plus the cosine of 1 divided by 20x. Okay, so that's our E function, and then let's add just a second function here. Let's add the, now t squared, so x squared, and then, where's the E button? There it is. E to the negative 0.3x. Boom. So there's our 2 graphs. Okay, so our first task was to interpret the meaning of and give the value of E5. So let's just get that value real quick. Let's trace the graph, and we need it to be at x equals 5. So when x equals 5, the E function is 3.2. That can't be right. We need some more digits here. So like I've yelled at you all year, when you're approximating something, got to be correct to at least the 3rd decimal place. So I'm going to increase my display digits here because the computer goes to default every time. So now I got to trace again. There we go. So 3.20, let's round that up to 3.205. And let's make sure we report the units here. So it was in cubic feet per hour. So that'd be feet cubed per hour. And what that means is, like if we were to put this in a sentence, at t equals 5, I would say snow is accumulating. You could say on the driveway or something. You could just say snow is accumulating at a rate of, I guess I didn't need to underline that here, at a rate of 3.205 feet cubed per hour. The word rate might not be very important to you right now, but it definitely will be by the time we're deeper into this class. Why did 3 go away? Okay, whatever. Okay, this is going to get real annoying if the computer keeps wanting to scroll to the top. Boom. Okay, question B is, using correct units, interpret the meaning and give the value of these two functions subtracted, and they're evaluated at the same time. So we can do this on the calculator. So let me show you how to do that one. Let's just see how I punched them both in here. Let's go back to the home screen. And let's open up a calculator here. And did you know that if you press the button right above 9, it stands for variable, you can call any of the functions you entered. So F1 was our function for E. And if you put a number in parentheses, that's where it's going to evaluate the function. So F1 of 5 for me is really E5 minus then R5. So I'm going to hit the variable key again. Now my R was function 2. For you, it might be something else. It might have been your 8th and 9th functions you plugged in your calculator, whatever. Doesn't matter. And that is negative 2.373. Okay. Negative 2.373. And again, we got to report in correct units. So it was cubic feet per hour. And let's think about what this really means. So E was the rate of snow accumulation. R was the rate of snow removal. So wouldn't amount that's coming in minus amount that's going out just be the amount of how the total amount is changing? It would be. So let's say at t equals 5, the amount of snow on the driveway is, now you can either say one of two things here, so I'll give you both. You can either say it is decreasing because your original number is negative by 2.373 feet cubed per hour, or you can say it is changing by negative 2.373 feet cubed per hour. The important thing is that you don't say it's decreasing by negative 2.373 because that would be a redundant. Technically, that would be basically a double negative, and how do you decrease by a negative amount? That's increasing. So be careful. Pick one of these ways and just stick to it. Doesn't matter to me. Okay, part C, using correct units, interpret and explain the meaning and give the value of R prime of 7. So I'm going to work that one down here because I ran out of room. Let's reach for our calculator. Now R was the second function I plugged in, so I'm going to go menu, calculus, I need my derivative. The variable is x. We're using when x is 7. And then in this box here, again, I'm just going to punch in the function that we used earlier. Oh no, maybe this doesn't work on this style of calculator. That's going to be really embarrassing. Nope, it did work totally just fine. Just make sure you leave the x in there since we're saying, hey, this is where I want you to do it. Okay, so the derivative of our R function at x is 7 was negative this. So equals negative 0.08, and then I think the last one rounds up to 6. It does. Now let's talk about units here real quick. The original thing was in feet cubed per hour, but the derivative is really the slope, and slope is a rate of change. So the derivative of a function is telling you how it is changing, right? It's got to be changing with respect to something. Every time you take a derivative on any kind of function, you are introducing another factor of time. So here, the derivative of the function r would be, how is the rate function changing? Well, now it's got 2 factors of time instead of 1, because you're describing how the first one is changing every hour. So again, I've got a way to translate that into English here for you. So we could say at t equals 7, the rate at which snow is removed is decreasing. So notice how, oh wait, that was the total amount before. Okay, ignore me. The rate at which snow is being removed is decreasing by 0.086 feet cubed per hour. Or again, you could say, or changing by negative 0.086, whatever works. In other words, again, just trying to give you a different way to understand this. This is confusing. That would be each hour, the rate itself is decreasing by 0.086, at least at this specific time. That might have changed by the time we get to, oh, well, it's not t equals 3, it's t equals 7. That might have changed by the time we get to t equals 8, or even t equals 7.5. But right there at t equals 7, that's how the rate is changing. I know that can kind of be confusing sometimes, so please let me know if we can talk through this more in class. And don't you worry about a thing, Chicken Wang. We got some examples to practice tomorrow. Have a good one.